Real numbers and proofs. Integers and subsets. Natural numbers, given this symbol with a double-barred n, are the counting numbers. We start at 1 and we go up in ones, essentially forever. We could represent this set in an ellipse like we do on a Venn diagram. The integers, given this symbol, a double-barred z, are whole numbers including 0. So they go all the way from negative infinity to infinity and therefore contain the natural numbers. The natural numbers are a subset of the integers, which we can show like this. Some common subsets that we use when talking about the integers are the positive integers, z plus. Note that's the same as the natural numbers. And the negative integers, which we indicate with z minus. On this diagram, the outside region contains the negative integers and 0. We sometimes split them as even numbers. That's an integer divisible by 2. When we're doing proofs, we often need to write that as n is equal to 2k, where k is an integer. Think about substituting different values of k in here, you'll just get even numbers. Then we have odd numbers, which is an integer not divisible by 2. The way we often represent these when doing proofs is that n is equal to 2k plus 1, where k is an integer, or sometimes 2k minus 1. So another way of splitting the integers is to split them into the even numbers and the odd numbers. Some other definitions that we need to be aware of. A perfect number is a number where the number is equal to the sum of its factors excluding itself. An example would be 6. The factors of 6 are 1, 2, 3 and 6. So if we add up the 1, 2 and 3, we get 6. So 6 is a perfect number. A deficient number is where the number is greater than the sum of its factors excluding itself. An example there would be 8. The factors of 8 are 1, 2, 4 and 8, and if we add up 1, 2 and 4, we only get 7. So 8 is a deficient number. An abundant number is where the number is less than the sum of its factors excluding itself, and an example there would be 12. Amicable numbers are pairs of numbers where the sum of the factors for one number excluding itself is the total of the other number. An example, 220 and 284. Let's just look at that. So if we examine 220 and we find its factors, so we can split that into 2 and 110, and of course 2 is prime, so we'll ring that. This splits into 2 and 55, ring the 2. That splits into 5 and 11, so both of those are actually prime numbers. So 220 is 2 times 2 times 5 times 11. From this we can find all of the factors. 1 is a factor of everything. We've got 2 here. Taking the two 2's together gives us 4. We've got the factor of 5. Taking a 5 with a 2 gives us 10, and so on. Taking all the possible combinations of these gives us all of the factors. If we add those up, excluding the 220 itself, we get 284. In a similar way, the factors of 284 are these here, and if we add these ones, we get 220. A prime number is a positive integer with two distinct factors, 1 and itself. For example, 3 has a factor of 1 and a factor of 3, and no other factors. This is why 1 is not a prime number. It doesn't have two distinct factors. A composite number is a positive integer with more than two factors. In other words, numbers are either prime, composite, or 1. And we're talking about positive integers only here. 1 is a special case, which is neither of these. A Mersenne prime is a prime that can be written in the form 2 to the power p take away 1, where p itself is a prime number. Here's some examples. P is 2. 2 squared take away 1 gives us 3. So 3 is a Mersenne prime. P is 3, we get 7. P is 5, we get 31. P is 7, we get 127. All of these numbers are primes. But not all Mersenne numbers are primes. There's no formula that exists that just gives prime numbers. For example, 2 to the 11 take away 1 is 2047, which is 23 times 89. Prove that when an odd and an even are added together, the result is an odd number. So let's define our odd. 2n plus 1, where n is an integer, is odd. We know that 2n would be even, adding 1 gives us an odd. 2m, where m is an integer, is even. We have to use two different letters n and m, as our odd and even are not necessarily related or anywhere near each other. So we use different letters. If we saw the word consecutive in here, we'd base them on the same letter. Now let's add them. 2n plus 1 plus 2m is 2n plus 2m plus 1, which is 2, n plus m plus 1. And that's definitely odd, because this part is even, and then we're adding 1. Now in part B, we want to show that when two even numbers are multiplied together, the result will always be even. So, let's take 2n, where n is an integer, and 2m, where m is an integer. If we multiply them, we get 4mn, which we could write as twice 2mn, and since it's a multiple of 2, it's definitely even. Both of these proofs are what are known as direct proofs, and we can now do exercise 7.01 on page 246.